So now we'll be going over what's called exact equations. Previously, we went over how to solve separable differential equations as well as when you weren't able to separate the variables. Now there's another way to solve differential equations. So let's go ahead and consider a form. Now let's consider a differential equation of this form. You have a function m with respect to x and y dx plus a function n with respect to x and y dy is equal to 0. Now, what exactly is an exact equation? Well, by definition, an exact equation meets the criteria of the partial derivative of m with respect to y must be equal to the partial derivative of n with respect to x. Now this is what an exact equation is. It must meet this criteria. Now, for if for whatever reason it is not equal to, this would be considered a non-exact equation, and we'll be going over in a different video on how to solve those. But for now, we'll be going over exact equations. So let's go over this example to test if this differential equation is in fact exact, and then we'll be able to solve this differential equation. So for this example, we have 5x plus 4y times dx plus 4x take away 8y cubed times dy is equal to 0. Now, of course, as you can see the form above, you have your function m here and you have your function n here. So for to test for exactness, we just do the partial derivatives of n with respect to y, as well as the partial derivative of n with respect to x, and we must make sure that they are equal to in order for them to be exact equations. So let's go ahead and do that. So the partial derivative of n with respect to y is equal to 4, and as well the partial derivative of n with respect to x is equal to 4. So these two are equal to each other, therefore this is in fact a exact equation. So now that we see that it is in fact exact, we're able to utilize this method that I'll be showing you. Now keep in mind I won't be proving this method, but I will be showing you how to utilize it. So if it is exact, that means there exists some function, let's call this function u, such that the partial derivative of that function u with respect to x is equal to that m function, as well as the partial derivative of u with respect to y is equal to the n function that you see above. So now from here we have the partial derivatives of u with respect to x as well as respect to y. From here, all we have to do is integrate, and let's go ahead and do that. So let's start out with the partial derivative of u with respect to x. So we integrate both sides, and since this is with respect to x, let's go ahead and do that. So you have the function u with respect to x and y is equal to 5 halves x squared plus 4xy plus some function, let's call this gamma with respect to y. Because of course you took the partial derivative with respect to x, and if you had some y variable here, it would be treated as a constant, therefore it will be zeroed out. This is why you have this function. Now let's go ahead and do. So now that you solved for one of these, now all you have to do, you have this function u with respect to x and y. All you have to do is get the partial derivative of u with respect to y, and you have this as well. So let's go ahead and get the partial of this one. So the partial derivative of u with respect to y is equal to, this is held constant, so it's 0, plus 4 is 4x plus your gamma function, the derivative of this gamma function with respect to y is equal to, since you already have this, you just equal it to the other side. You have 4x take away 8y cubed. So the 4x cancels out, and your gamma prime y is equal to negative 8y cubed. And now from here, you integrate this gamma function. Then you have your gamma of y is equal to negative, this one's 2, right? Y squared plus your arbitrary constant. So now you go ahead, plug it in here. So now you're finally left with this u function with respect to x and y is equal to 5 over 2x squared plus 4xy, take away 2xy squared plus your arbitrary constant is equal to 0. So this is your solution to the differential equation. So now for our next example, we have 1 plus the natural log of x plus y over x dx is equal to 1, take away natural log of x, dy. So first step is to get it to your standard form. So you move the this side to the equation on the other end. So now from here we can see what our m function is as well as our n function. So let's first check if this equation is exact. So our partial derivative of m with respect to y is equal to 1x, and our partial derivative of n with respect to x is also equal to 1x. So they in fact are exact. So from here we could go ahead and equate the function u with respect to x is equal to m, as well as our partial u with respect to y is equal to our function n. So since we checked for exactness, we have our partial derivative of u with respect to x is equal to the m function, and our partial derivative of u with respect to y is equal to the n function here. Now from here, we just choose either one or the other to integrate and solve, and then get the derivative and get our function, our solution to the differential equation. Now for this one seems to be a lot more straightforward, gain the derivative of this one. Let's go ahead and do that. So we have our function u is equal to y ln of x take away y plus some function gamma with respect to x. Now from here you get the partial derivative of this with respect to the other one with respect to x. Since we already have this solution, let's go ahead and get this derivative. So our partial derivative of u with respect to x is equal to y over x take away our derivative of the gamma function with respect to x. And of course this is equivalent to that. So we put it on the right hand side here. And from here, you cancel this, cancel that, or one thing to mention, this in fact is a positive sign, not a negative. So your derivative of this gamma function is equal to 1 plus ln of x. So all you do is integrate here. So our gamma function of x is equal to x plus x times natural log x, take away x. And this is solved using parts by integration, which of course this is equal to just x natural log of x. And now you just plug it into your function u here. So we have that u function, which is equal to y natural log of x take away y plus x ln of x is equal to your arbitrary constant, which we just moved from one side to the other. I forgot to mention this arbitrary constant I forgot previously. And we just manipulate this to get the y on one side, and this is your solution to the differential equation. So now this is how you solve exact equation. It's another method of solving differential equations. Previously, it was a separation of variables. Then the other method is when you weren't able to separate the variables. Now this one is another method you could utilize. Now keep in mind we did not go over how to solve non-exact equations, which we'll be going over in the next video.